Okay, let's continue the bridge modeling. I select deck roadway, and in this part you should enter the distance between upstream cross section and the deck. Okay, let's assume that this distance is about. Okay, I want to interpolate. Let me check. Is it possible or not? Okay, we can't. Okay, let me do. Okay, it's not problem. Okay, I want to enter the number of centimeter, but as I told you before, you should enter smaller value for this section. The width is the roadway dips in direction of flow, and I want to enter, for example, the number 5 meter. And this is a wear coefficient, as I told you, when the water start to overtopping from the bridge, the model uses this value for wear coefficient and flow from the flow upper the bridge. And the wear coefficient range between for OG varies between 3 and 4, and for broad crested varies between 2.5 to and 3.1. For example, I want the average value of 25 because in most case studies the road or deck behave like a wear, not like a OG waves. Okay, in this part you should define the shape of your road deckway. In this figure I created the critical points and required points from this point to this point. Okay, I should enter the station from 0. Okay, the high chord, you should select the elevation of the high chord. Let me select the number of 9. Okay, what's the low chord elevation? Assume that the thickness of road or deck is equal 1 meter or lower than 1 meter. I enter, for example, the number 0.5, and you should enter the elevation. And the difference between these values represent the thicknesses of the road or deck. Okay, this is the upstream, because in this case the both upper and downstream are the same. You can use these values for upstream and downstream parts. Okay, the last number, the station is 20, and you can enter again these values for high chord and low chord, and click copy upstream to downstream, and it's automatically copy these values to the next cells. Okay, if you have embankments, you can enter US embankment side slope and downstream embankment side slope. And in this case, we assume that we don't have any embankments. For additional wear data, you can set the maximum submergence. For example, in this case, HEC-RAS assumes that the number of 0.98 is the maximum submergence value. It assumes that when the water depths at the upstream of cross station, let's assume this is the water depths, and this is the distance between the road deck, under off-road roadway, and the bed of the riverbed. Okay, when the ratio of these depths to these depths is higher than the maximum submergence, the model automatically start to use pressurized flow equation, as I told you in the previous video. Okay, you can select where selected shape, for example, broad crested or OG. For OG, you should enter different and more parameters. I select broad crested, and the minimum flow wear elevation can be set as number 9, because the high chord can be used minimum wear flow elevation. I select OK, and you can see the shape of road deckway. Okay, the second important part of a bridge is the pier, and you should select pier from the left sidebar, and in this editor or pier data editor you can define different shapes of bridge. For example, I want to model one bridge in this station, the second in this station, and the third pier is located in the, for example, the station of 12, excuse me. Okay, when you cross the points, you can see the values in the lower section or lower parts. Okay, the station of this point is equal 57.50. 7.50. For center line station downstream, I can enter this value. Okay, in this part you should enter the pier width. For example, from the elevation of 5, I want to enter pier width, for example 1, and this is 1. And for elevation to top of the roadway, you can select the maximum elevation and copy up to downstream to automatically copy these values to the remind cells, and then press OK. Okay, this is a little big pier width. Let me decrease the pier width, and I want to use these values. Copy to downstream. Okay, let me to increase a little more, 0.3. Okay, these are elevation and these are widths. You can use different pier widths, and in the second and in the next parts of this course, I want to learn you how can you use arc shape or other shape of the piers. Okay, I think this is good for the pier width. Okay, again select pier, and in order to manually enter the parameters, you can select copy and change the center line station downstream to another number, and then press OK. You can see another pier is appeared, and the third, select pier 2 and select copy and enter value 12.5. Okay, I think this is a good shape of piers, and you can define new piers in this location or in this location or other location you want. But I can't want to model pier in this location. I want to use abutment for this section and cover these parts. Okay, in HEC-RAS you can use a sloping abutment. Okay, in this part I want to cover this opening area because I want to use abutment from the left, in the left side and in the right side. Okay, station, interstation 3, elevation from the left to side. Elevation can be used 9. For this station, you can use 5.5 and again 9. And finally, for lower parts, you can use number, for example, 6. Lower and this value, let me to enter 7. Copy up to downstream and you can see this shape. Okay, if you want to change the values, you can go to this part and enter a lower value for elevation. Okay, I think this is good. Okay, for the rightest loop, you can do the same task again. And for this, for the right part, I start to enter values from down to up and left. Let me to explain in the word. For left side, you should enter station elevation from left, right, and down. While for right part, you should enter value from down, top, and left, and model automatically connects these parts. Excuse me to these shapes. Okay, from this station, 14.5, elevation is 7, 8, station 45, elevation is 88.5, and the right maximum station is 20, and this is 8.5, and copy to downstream. Okay, as you can see, we can easily create a bridge model in HEC-RAS. Okay, in this picture you can see the location of bridge. Because I entered the lower value for this part, for this section, and the bridge is near to the upper cross section. And by changing this value, you can change the location of your bridge through between two cross sections. For example, I want to enter 40 for distance, and you can see the cross section is located almost between two cross sections. Okay, but as I told you before, you should create cross sections near the bridge, but in this example, we didn't consider this issue. Okay, that's time to run the model. I save the model. These are the flow values, and these are the boundary condition values which are discussed in the previous part of this course. Okay, go to the steady flow analysis and select the compute button, and model starts to run. Okay, the complete process has finished. Okay, go to the cross-section profile, and you can see the water surface around the piers and abutments in the upstream and the downstream. Or you can use a profile to see better representation of your bridge location. As you can see, when the flow around the piers drop because the effective flow area is decreased and the velocity increase, and it leads to decreasing the water surface profile. Okay, let me back to the geometry data model. In bridge and culvert section, you can use different loss calculation methods. Select bridge modeling approach. As you can see in this section or in this window, you can select different methods. For example, momentum, Yarnell, and whisper. And you can set highest energy answer or select one of them. In each time, you can use only one of them, one of these methods. You can use all them and run the model simultaneously. In each case or in each run, you can use one model. Okay, for example, I want to use momentum and select momentum. This is for high flow methods. Energy only, pressure and wear. And this is, for example, you should enter coefficient drag coefficient and maximum low chord for your bridge. But I recommend you to use energy or a standard step method because this is a suitable and appropriate method in natural rivers. Moreover, for using momentum, we need a coefficient drag or drag coefficient. As I told you in this figure, you can use drag coefficient. For example, I want to use this value. And when you select this option, the model open this manual and you can use these values. Okay, I select this method for bridge 1 and select OK. Save model and again run model for new loss computation method. Okay, you can see the water surface in the cross section upper and down parts of the bridge. This is a longitudinal profile and variation of hydraulic parameters. For example, for top width, let me select one profile and right click and select plot variables and only show top width. As you can see, in the top upstream of the bridge, the top width increase, and in the downstream start to decrease. Also for water velocity, I select total. Let me total velocity. Okay, as you can see, when the model reaches to the bridge location, the velocity starts to decreasing, and after that starts to increasing. This part for downstream, and this part is for upstream. Okay, and in the summary output table, you can find the variation of hydraulic parameters upstream and the downstream, and you can compare these results with the natural rivers to show how can hydraulic structures and bridge can affect on hydraulic parameters. And in the 3D multiple cross section, you can see better shape of your bridge, and you can rotate. Let me to zoom in. Okay, you can see the 3D animation of your bridge location. Okay, some important parameters. I explained more important parameters of bridge modeling. Let me introduce some remind parameters. Okay, in bridge section or in bridge data editor, there are some parameters. For example, debris width and debris height. What's this? HEC-RAS can simulate the effect of, for example, tree or other for example, other features in flood. Let me to create this. Assume that these are the piers of bridge. And in flooding conditions, the flow contains several materials, for example, trees and other materials. And these materials cannot cross between the piers, and look, and it starts to float over the water, and these materials decreases the effective flow area. Okay, HEC-RAS can consider the effect of debris flow on the performance of hydraulic structures. Therefore, you can enter the rectangle shape of these debris flow. Let me assume that the debris width is about 1 meter and debris height is about 1 meter, debris width is about 2 meter. And apply floating. Okay, let me to enter this value for all piers. Okay, again save the file and run the model again. This option is useful in forest or in forest in rivers which is located in forest or jungle parts. Okay, as you can see, the debris flow decrease the effective flow area and the model starts to backwater. Let me to select other profiles, select all. Okay, you can see different flow values. Let me increase the number of flow profiles. As you can see, in this case, the debris flow increases the backwater in the upstream of bridge. Okay, as you can see, the drop in water surface is considerably increased, and also the hydraulic parameters, for example Q50. Let me to clear this and select velocity total. Okay, as you can see, in the existence of debris flow at the upper parts of the bridge, the flow velocity started to decrease, and after that starts to increase, and this is the effect of debris flow. However, we can define or save this section as, let me enter a new name, plan underline debris. Okay, let me debris. Let me compute again. Okay. Let me to save geometry data as another name, my geo base. Okay, and go to the bridge culvert, pier, and remove or all of, and remove these values. And remove, select. I want to compare the effects of debris flow and base plan. Save plan as, for example, base 1. Base 1 and select compute. Okay, close, and you can easily compare their results. Okay, for third flow values, I right click on this window and select plans and select the plan debris. Okay, as you can see, in the base, in the without existence debris flow, the water surface elevation is this, and in the existence of debris flow, the water surface flow decreases a little bit. And this is a longitudinal profile, and you can compare in the absence of debris flow and the existence of debris flow. As you can see, in the existence of debris flow, the water surface profile, the backwater depth is higher than base scenario, and the water surface at the downstream is have a higher speed due to the lower flow area. And in the hydraulic properties, we can compare variables, for example, total velocity total. Okay, this is completely clear that debris flow can change flow velocity values. Okay, I think this is enough for bridge modeling in this section, and you can use this video or this processes for natural rivers. For example, you can use all those SRTM DMs and extract channel geometry of a real river, and then use these processes to model your bridge. In the next section, or in the next part, we want to model arc shape bridge, and then go to the model dams, inline structure, and then go to the simulation of culvert in rivers. Okay, I hope have a good time and happy to river engineering using HEC-RAS. Bye bye.